Okay. Hi, everyone. My name is Stephanie Rosenthal. I'm a research scientist here at the SCI. And so this is joint work with two Carnegie Mellon faculty members, Professor Sid Srinivasa and Professor Manuela Veloso. And we have 4 students that we're co-advising together. So the main challenge here is that in the last, I would say, 5 to 10 years, we've had just this huge increase in sensor capabilities. Here's, I believe it's an Uber self-driving car here in Pittsburgh, and this was never possible even 5 years ago. And the challenge with these robots today is that there are just so many different algorithms that are going on that we have no clue what the robot will do in any particular scenario. And so here's the state-of-the-art solution to that. There are 2 people who sit in every self-driving car, one who keeps their hands on the wheel, and one who watches the sensor data to make sure that they can figure out what's going on. And that's a little scary, right? At some point, we have scaled from 1 driver to 2 instead of from 1 driver to none. And so the whole job of this project is to try to get the robot, the car in this case, to actually generate by itself an English explanation of what it's doing. If we can generate that in English, then hopefully we don't need a person just sitting there watching that sensor data. But if something happens, the robot can say, here's what happened, it's okay, I know what I'm doing, or not, and we can continue on our way. So for the remainder of the talk, I'm going to keep using self-driving cars as the example, because I think it's a good one for us, but practically speaking, I use different robots for the work. So here's our scenario. We have a self-driving car in the middle of all these other cars. There are 5 other cars. There are some pedestrians on the side. And this car is driving in between the 2 white lines. The question is, why did the robot do that? So I'll describe for the remainder of the talk how we get that robot to describe why, indeed, it is where it is. So there are lots of different reasons it could be there. It could be a sensing reason, right? It could just not see the white line. It's trying to stay in the middle of the lane. It could be merging left or right. We don't know. And it could just be trying to prefer driving fast, and so it's passing the car, right? There are lots of possible reasons, and that's why we want to generate this English explanation. So the first thing that we did when we started last year was actually what we called actuation verbalization. And the idea with actuation verbalization is that we maintain a vocabulary, which I'll show you in a second, of all of the different things that this robot can sense. And then given a path or some execution that this robot's doing, we just translate little pieces of that path into English sentences using our dictionary, 1-to-1. And that actually does pretty good. So here's all of the labels, for example, in this scenario. They're maybe a little small, but there are peoples and cars, signs, fire hydrant, lane boundaries. All of those things are things that we can keep in a labeled dictionary that the robot has. And then when we have a particular action, the robot knows it's moving left or moving right or staying where it is. It can actually write that in English as well. So we've actually done this on 2 different robots. First is the one on the right is Cobot. It's a Carnegie Mellon robot by Manuela Veloso. And everywhere the Cobot moves in the Gates building, it can generate an English explanation of where it went. And here's a robot boat example. We are also collaborating with the University of Iowa, and they have boats to help us search and rescue, and their search and rescuers, I guess, they're unable to stay in the water for very long, but if you can send in a boat, that helps a lot if they trust that boat. So now we have the boats actually explain what they're doing in this iPad interface so they can see where it's gone before and where it's going now. Okay. So this is actually running code. You can do this too. So that was great. We're like, okay, we're done. No, we're not done. There are lots of challenges in exactly what you write down for a person and what the dictionary says, and personal preferences as well. So the first challenge that we tried to tackle this year was different people's perspectives. So if you're in the car and just concerned that the robot's not going to hit you, you might need different information than the policeman who is in charge of making sure that everyone around them is safe and possibly needing to pull that car over if it can't get further, if it's not making good decisions. Actually what we did with our verbalization algorithm is that we parameterized it. We can talk about different levels of abstraction, so the robot can talk in terms of GPS coordinates versus lanes and roads and intersections. We can be very specific, so we can give you like a paragraph output versus one sentence. So if you're in the car, you probably don't want to read a one paragraph explanation, but if you're the police officer, you might. And then locality, so perhaps you only want to know what's going on in this scene, or you might want to know what's going on with that robot for the last hour. And all of those things we can vary at this point. So we can actually generate explanations that say, like, I'm merging left in anticipation of a left turn, versus I see 5 cars and there are 2 or 3 people. And I'm uncertain of whether the car on the left will merge into me. All of those things are things that we can now verbalize based on these parameters. If you have a set of parameters about a person, like the policeman or our car driver, we can actually automatically generate different explanations per person. The next one is scalability. So it's one thing to label everything about a road for the self-driving car, but there are lots of different robots. There are robots in parks, there are wheeled robots and drone robots, right? There are lots of different types of robots, and to scale this idea of a dictionary is sort of infeasible to have a programmer write in all of those things. So what we decided to do instead is to actually crowdsource all of our dictionaries. So we generate scenarios, for example, a car turning left or a car with a car turning right, and then we get thousands of people for very cheap to write what's going on in that scenario, and then we can map the words that they use and also the patterns of speech, or the patterns of explanations, by first ranking which ones are the best and then finding those patterns. So we're still working on automating this procedure, but we've actually been able to do this on multiple different types of robots as well in different scenarios, so we no longer have to generate that dictionary by ourselves. So let's just put this together, right? We have a vocabulary, and now we have explanation patterns generated by the crowdsourced people. And then at runtime, we have a robot path, which is typically logged in the robot system, and we can pull that out, and you have a sequential set of actions and what it saw at each of those steps, and we can map each of those things together. So what I didn't say at the beginning is that this is actually a 2-year project, and I'm only 1 year in. So we have lots more to do here. The next step that I'm looking at currently is what the action is versus a question of why. So the title of this project is Why Did the Robot Do That? Not What Did It Do? And so a verbalization right now is really a what did it do? It was changing lanes. Here's what it saw. It's not, I prefer to go fast, right? Because if I have a preference like that, then whatever action it's taking, we know that it did it because it's optimizing for that, right? So in this example, the what is, I used my signal and I slowly merged from the right lane into the left lane, but the why is that I'm about to turn in the future, and so my algorithm says I need to merge left, to turn left at least 500 feet in advance. So now the next time that a person sees this robot, they'll know what to do instead of just the what example. So we're working on that. And the other question is, as Eric introduced at the beginning, this is all about trust. So right now we know, in some sense, that we can actually translate these actions into English sentences. The question is the police officer, after seeing that explanation, now willing to turn his head away from the car and talk to another person on the street? Or does he have to watch the robot? If he has to watch the robot, then we haven't done much better than a regular car again. So in this case, the measurement is called neglect tolerance. It's actually a measure of how often you're willing to look away from the robot in order to allow it to do what it's doing by itself, to actually be autonomous. So you saw the boat video before. One of the main things we're measuring on that iPad is your willingness to not watch that iPad anymore, but to actually go about other search tasks instead of watching this robot. We can do that with lots of other robots as well. And then one more pitch. I think my time is almost up. My next project that I should start to be presenting next year is called What Will the Robot Do Next? So the idea here is that we should be able to make the robot perform paths or act in a way that's predictable even without explanations. So the explanations are useful when you just can't do that, but we're hoping to be able to actually optimize for better paths in the future. So with that, again, my name is Stephanie Rosenthal, and I think other questions?